You are climbing a staircase. It takes n steps to reach the top. Each time you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? So this is a pretty cool problem. And if you haven't tried this one before, I would say really give it a shot. I'll leave a link to this problem in the description. So give it a shot. And I'm assuming that you've given it a shot. So the answer to this problem is pretty straightforward. It involves recursion, but it takes it a step further. So first, let's talk about recursion. So suppose we had a function called climb steps. Climb steps. It's going to take an int. Let's call it x. And all x is going to be is the stair that we're going to be climbing to. So stair climbing to. And again, at any time you feel inspired, you think that you figured out the answer, feel free to pause this video and give it a shot. So x is going to be the stair that we're climbing to. And looking back at our problem description, we can only climb 1 or 2 steps at a time. So the answer to this actually is almost the same as Fibonacci. Climb steps is just going to be return, climb steps, x minus 1, and climb steps x minus 2. And why does this work? So suppose we knew the answer to the one before, x minus 1. We can use our one step to get to the, so let's draw like a staircase real quick. Suppose this is x, and we say that we know this one and this one already. So this is going to be x minus 1, x minus 2. When we're at this step, we can just use the one step to get the level that we want. And when we're here, we can just use 2-step. So the amount of solutions that we have here and here, we just add them together and we get our solution for x. So it's pretty straightforward. But as we'll see, and if you remember, this function can get pretty complex pretty quickly in terms of recursive calls. So I actually have the solution written out already. Don't look at all this. Let me just minimize this. So right now, I have something called top-down without memo. Don't worry about the name description. Just understand that this is our basic recursive call. So if I try running this by itself, submit. You'll see we get time limit exceeded. So it takes way too long for this to run. But why is that? Again, if you look back to Fibonacci, it takes a really, really long time for this to execute. So what is our solution? We introduce something called memoization. So let me write that down because it's not memorization, it's memoization. And the idea behind memoization is every time we do a recursive call, we store this answer in some sort of array or other sort of data structure. So this prevents repeated recursive calls. So again, I have the answer here. So let's take a look at it. by the way, this gets into the realm of dynamic programming. And what is dynamic programming? You can think of dynamic programming as recursion with memory. So we start to write down all of our answers as we do it. So let's look at a more straightforward example of this answer. So with bottom up, let me hop back over here before I start explaining this. So bottom up is going to be taking a array and let's just say this is of size, let's just say this is size x plus 1, just to make it easy. So this is our final cell. Let's just say we ignore 0. And when we're at 1, we're on our first step. So there's only one way to get to 1. And then on our second step, there's 2 ways to get to this one. We can either go from 1 here, or we can just jump from 0 to 2. So now once we get to any other cell, let's just say 3 for right now, it's going to be the same thing as climb steps. We're just going to look back to our previous steps and say the one right before it and 2 right before it, add these together to get our third one. So as we're doing this, we save a lot of time not recalculating all these things. Because otherwise, I mean, if we were at like, let's say we were at step 5, we would have to call to step 4 and step 3, and 4 would have to call to 3, then 2, and then 1 and 2. So these are all going to be called a lot, and it's the same thing that's called over and over again. We don't have to waste time with all of these. We can just say, we already calculated this. We can just use that answer again. So that's how bottom up works exactly. We just work from the bottom, continuously building up our way to the top. So let me show you that. We're going to start with our first 2 cases where it's n equals 1, n equals 2. We already know those. It's going to be 1, 2. We're going to create a new array on heap because, again, this is going to be something that we're not going to know at runtime. And looking at this, all we're saying is if we haven't calculated, so all we do is we just say from 3 until our last value, n plus 1 in this case, we're going to be calculating our number for our array using our previous 2, and then just return that answer. So if I just uncomment this, this is bottom up. If I submit this, it should run. All right, cool, it's accepted. So now let me show you the last one, which is top down. So top down, down. Let me zoom in a little bit. So top down is going to work in the opposite way. We're still going to have an array. And we're still going to have it as it's x plus 1. And we're still going to have, this is 0. It doesn't have to be. It's just going to be easier for understanding. 1 is going to be 1. 2 is going to be 2. And instead of working from bottom up, we're just going to start from here and just ask, all right, well, I want to know what this is by just looking at the previous 2, summing them together, and just returning to that. So again, this is going to be much faster, and it's going to work in comparison to our recursive call because of this again. We take out all the work that needs to be done. So let's hop back over here. And you'll see that this is going to be very similar to what we've done already. So right now I'm declaring some base cases. I'm creating a new array. And here, this is where this is going to be useful. We're just going to say, all right, if our number hasn't been initialized yet, if it's -1, we know that we haven't calculated it yet. So let's just set up our base cases, 1 and 2, and let's recursively call this, passing in both the number that we want and a pointer to our array. So, I mean, this is going to be all it is. Just return this value. And this value is just going to be this one plus this one. Take the previous two terms, add to get them together, store it in here, and then just return this. If you start to work through some of the logic of this, if we work at any numbers smaller than x, you'll see how this builds up from the top down, if that makes sense. And in case it doesn't, let me just rehash this. We're just going to say, all right, I want this to be equal to this plus this. And these might not be initialized yet. These might be -1. So what we're going to do is we're going to recursively call on this one then. We're going to say this is going to be equal to this plus this. And we're going to keep going down in this fashion until we finally get to our base case. And once we finally get our base case, we start populating this up again from the bottom up. And then we'll eventually get to this value, which is going to be our answer, the thing that we're going to return. And just to show you again that this does work, so we're working with top down now. Working with top down now, submit. And I'm going to post the code for this if you want to take a look at it for yourself in some greater depth. But I hope this was helpful for memoization and recursion.